Hi everyone, welcome to Telco Tech Talk again. Today we will be discussing part 3 of spectral efficiency. So we in the previous videos, the first two part of this series, we have touched upon what is the importance of spectral efficiency in a bit more practical way and where it's been applied, how it is benefiting us, where not only the telco, beyond telco, where it's been implemented and it's giving us the needed benefit. Okay, and in this video, as we discuss, we will touch upon how this gets calculated just for the theoretical purpose, for the interview purpose, if you want to have. Okay, and I would suggest you go deep into it, look for the calculators, create your own calculators. It's pretty easy. Okay, once you understand the concept, it should not take too much of an effort because by the time you reach to a concept of spectral efficiency, which means you have a good enough concept of LT bandwidth, channel, MIMOs, QAM, quadrature amplitude modulation, all those methods. And let's start. So spectral efficiency, as we discussed, is typically bits per second per hertz and can be calculated using the formula data rate divided by bandwidth. So what is data rate? And when we say data rate, how are we talking about overheads as well, like in LT or in any radio access technology, there will always be overheads. So we should be calculating spectral efficiency based on actual data or payload that which is being transferred over over any given channel. So which means essentially we need to reduce the overheads. So let's say after reducing the overhead, we have the actual data. Okay? So actual data flowing per second divided by the channel bandwidth is what gives you the actual spectral efficiency. We'll go get more details by the example of 4G. 5G, I will like you to try on your own. I'll only give the very short introduction on 5G calculation, but I would advise you calculate for 5G and let me know in the comment if you face any issues. So spectral efficiency in 4G, we know key technologies are 4G for OFDM, orthogonal frequency division multiplexing. I'm assuming as of now that you understand the concept of OFDM and MIMO. So OFDM example calculation, let's suppose 4G network achieves a data rate of 50 Mbps using 10 megahertz of bandwidth. So by using, and this data rate, let's say, assume that the data rate is considered after excluding all the overheads. So using the formula, our spectral efficiency 50 Mbps converting into BPS and 20 megahertz converting into hertz gives you the band spectral efficiency of 2.5 BPS per hertz. So which is pretty simple. So okay, what's new in this? Why there could be a question why we are reading this cross. So now let's say MIMO technology is there, which can be 4 cross 4. Okay, so if you have and it's a very simple way people can challenge. No, this is not the right way. You cannot be multiplied by 4. But if you have a spectral efficiency with, let's say, SISO, if it is 2.5 bps per hertz, with MIMO, it will be 4 into 2.5. Okay, this is just a theoretical concept. I'm not saying that it is foolproof, but yes, if you understand the concept of SISO, single input, single output, then you using multiple input, multiple output, 2 cross 2, 4 cross 4 can give you the very easy calculation. But theoretically, how we calculate spectral efficiency, how we increase spectral efficiency, we'll get into details of that. So theoretical calculation of spectral efficiency, let's say in LT, we have a maximum data rate, theoretical data rate possible with 4 cross 4 is around 400 Mbps. And as we understand, maybe you can read it through with different sources. The 25% are the overheads, and then that means actually means actual data rate is for user is would be 75%, which is approximately 300 Mbps. So this is not exactly 400. This is comes down to around 391 something. So for the sake of calculation, I'm taking a very round figure. So 400 Mbps approximately, turning into 25% overhead and 75% which is coming out as a 300 Mbps. So now applying the formula on this theoretical, we are getting 15 bits per hertz with 20 megahertz of channel. So this is, we can say, a theoretical spectral efficiency for a 20 megahertz channel in LT. Okay, and this could also vary depending on environmental condition, SNR, and all that. So same way, we can have a spectral efficiency calculated for a uplink as well. Now, how to improve spectral efficiency? We have discussed in the previous videos. In case you have not seen, please touch upon those videos in the same series. We are discussing higher the better is. So which means that the higher the value of the spectral efficiency, better it would be, and higher the degree of QAM can improve um, SE. So let's take example of uplink SE improvement. In uplink, we have an option to use higher QAM. Below is the different SE values you can achieve based on higher QAM. So I'm giving you the figure, okay, based on my calculator, that how much it will different if we use QPSK in uplink, if we use 64 QAM in uplink or 16 QAM in uplink, what would be the difference? So you see, we have selected band, which is band 1 of 20 FDD 2100. Maybe we can have another video where we explain the bands, LT bands, 5G bands. Okay, uh, write me in comment if you want that video. Bandwidth, we consider 20 megahertz. Now with this bandwidth and frequency band, let's say modulation scheme is first QPSK. So with QPSK 20 Mbps, what we can achieve in uplink throughput. This is a theoretical. Let's not apply MIMO in uplink for now. Okay, so 1 Bps is what we can max theoretically achieve. And and similarly with 16 QAM, we reaches 50 Mbps of throughput, 2.5 Vps hertz, 75 Mbps with 64 QAM. So we can say it's almost the 3 times or the 4 times between the difference of spectral efficiency uh, if you use QPSK and if you use 64 QAM in uplink. So it's a huge difference. So this is where operators tries to pitch in if you can, and on top of it, if you can reduce SNR with 64 QAM, which is a bit challenge, but you can achieve a better spectral efficiency. And this also gets maybe decrease somewhere sometime. Let's say in downlink, PRB utilization is high or anything. There are so many KPIs factor. We can get into details of those impacts. Maybe some other videos. Write me in comment if you want to discuss on that. In downlink also, we have, along with QM, we have MIMO as well. So with, let's say, for 2 cross 2 MIMO and with the same band, we achieve right from 5 Mbps to 10 Mbps, and with 4 cross 4 MIMO, we can go up to 20 Mbps. So with 256 QAM, we achieve, like, if a theoretical 400 Mbps, including excluding everything. Let's say I'm not counting any overheads, I can achieve 20 bps. But again, we 15 bps is what we discussed. Probably we will have in uh, after reducing all the overheads as a theoretical max spectral efficiency in LTE. Same way 5G. I'm not getting into details, but yes, let's say spectral efficiency. Uh, Sorry for this typo. This is 1 into 10 to the power 9 because it's 1 Gbps, not Mbps, and with again 10 to the power 6 hertz. Then so 10 bps. Oh, you people might be saying it's lesser than LT. No, there are many ways we can achieve more throughput, and we can have much higher uh, B spectral efficiency in 5G, going up to 30 bps as well. Okay, and with advanced modulation, let's say data rate can also be calculated if we have the spectral efficiency. Of course, this is understood at this level. So if you have a spectral efficiency given, let's say 15 Gbps, and you have 100 megahertz of channel, we get the data rate of 1.5 Gbps. So there is a reverse calculation also possible. This is all what I have in this part of the series, and keeping it very short so that you can just focus on the small concept. Anyone who is trying to get into the details, get into the details of the concept, this concept can, go through all the three parts of the series. You can refer, you can subscribe to channel, and just suggest me what the next topic you want to learn. I'll try to publish the video on that. Thank you. Signing off.